Okay, we're supposed to find the center of mass, the position of the center of mass of this plate. I'm going to start by defining a Cartesian coordinate system. I'll have x to the right on the page and y toward the top of the page. What I'm going to do is arbitrarily divide this shape up into pieces whose centers I can tell by inspection. Since it's a uniform plate, the center of mass will be at the geometric center. So I'm going to look at this rectangle right here. I'll call that number 1. Its center will be about right there. We got to figure out where that is. I got a bottom rectangle down here. Could have cut it up differently. I think the other natural way would be 2 longer vertical rectangles and a short rectangle in here. But I arbitrarily chose to go this way, and the center of mass of this part, I'll call it number 2, is going to be right there. We got to figure out where that is, and then find out where that one is. So by inspection, we can determine where the centers of mass are, and then we'll do a weighted sum to get the center of mass of the whole piece, and we'll talk about exactly how we're going to weight those pieces. Alright, let's get center of mass of number 1 first. It's 5 centimeters wide. It's a uniform plate, so the center of mass is going to be half the distance over to the edge of the plate, which would be this distance right here. So I'll call that x1 for the position of the center of mass of plate number 1. And x1 is going to be half the distance all the way across, which would be 5.0 centimeters over 2, or just 2.5 centimeters. Alright, how high up is it along the y-axis? I'll call that y1. y1 is going to be given, well, we go 5 centimeters up, and then half of this distance up here, which is 12 centimeters, so it'll just be 5 centimeters plus 12 centimeters over 2, and that's 6 and 5, 11 centimeters up from the origin. So 5 plus half of 12 is going to be 11 centimeters up. Then x2, this distance, well, let me go ahead and mark what that was. That was y1. That's what we just found. x2 will go all the way over to there. Well, that's half of 20 centimeters. Or just 10 centimeters. y2, how high up the center of this rectangle is. By inspection, it's going to be half the height of the rectangle. That's 5 centimeters over 2, or just 2.5 centimeters. Alright, then let's try x3. This was x2. x3 all the way over to halfway through this rightmost part there. x3 is going to be, it's the entirety of this length minus half of this width. So it'll be 20 centimeters minus half of this 5 centimeters right here. That'll be 17.5 centimeters. Alright, then we're going to need y3. By inspection, it's the same as y1. And that we found to be 11 centimeters. Alright, now, in order to get the position of the center of mass along the x-axis, I'll call it x bar. It's going to be the weighted sum, m1 over the total mass of the 3 pieces, times x1, plus m2 over the total mass times x2 plus m3 over m total, the total mass of the whole thing, times x3. Alright, now we got to talk about what those masses are. And the thing is, because it's a uniform plate, the mass of any piece is just going to be proportional to the area of that piece. So m1, for instance, will be equal to some constant times a1. We can call that constant the area density if we wish, the mass per area in kilograms per millimeter squared, for instance. It would, to get it, we would take the mass of 1 millimeter area of it and divide it by a millimeter squared, and then to get the mass of any piece we just have to multiply that by how many square millimeters there are in that piece. But we don't really need to name it. Call it the area density if you wish, or just say it's a constant. If we double the area, if we consider two pieces, one that's got twice the area of the other, it's going to have twice the mass. It's just going to be proportional to whatever the area is. So we'll use that fact. So m1 is some constant times the area 1. So I think we're going to need to know those areas. Actually, I want to write down what m1 over m is. m1 over the total m is going to be that constant that I just made up. We don't need to know what it is, and I don't think we care what it is because they didn't ask for the total mass. And we don't care what the mass of the pieces are, but it'll be whatever that constant is times the area, and then sigma 1 plus a1 would be the, well, let me replace that m total with what it is first. So I'll call it m1 over m1 plus m2 plus m3. That's what m is. It's the sum of the masses. And now I'm going to replace each one with the sigma times the relevant area. So this will be sigma 1 a1, and this will be sigma 1 a1 plus sigma 2 a2 plus sigma a3. And I said a1 up here, but there's only one sigma. There's only one kind of material, so the mass per area is the same for that entire plate, and hence I don't need any subscripts on those sigmas. And so that's on the bottom. What I can do if I want is to factor out the sigma. Sigma a1, that's sigma times a1 plus a2 plus a3. And then that cancels the sigma on the top, and so the ratio m1 to m is the same as the ratio of a1, the area of that one plate, the one I labeled 1, to the total area. Well, that makes life a little bit easier. I'll have the same thing for m2 and m3. I'll let a represent the total area. That'll be a1 plus a2 plus a3, which is width 1 times height 1 plus width 2 times height 2, etc. In fact, I think what I'll do is calculate the area of each one of these, and then I'll plug the values in there. So let's do a little bit of work on that. A1 is equal to W1 width 1 times height 1, which is equal to, and then I'll define what I mean by these W's and H's. This is W1, width of 1, and this is H1, which is 12 centimeters. It's also equal to H2, so H1 and H2 are both 12 centimeters. And then this is width 2, which is also the 5 centimeters. This I'll call, this is width 3, sorry. Because this was item number 3, so this is width 3. And this is H2, and W2 is the 20 centimeters. The width of object number 2, plate number 2, or piece number 2 is 20 centimeters. Okay, so what I wanted first was W1 times H1, which is 5 centimeters times 12 centimeters. Which is 60 centimeters. That's to, I think, 2 sig figs. We're going to need H2, and this guy, this 12 centimeters is actually the height of 3 here, so that's H3. So H2 is 5 centimeters. W2 is 20. 5 and 20. Let's see if I can remember those. A2 is W2 times H2, which is 20 centimeters times 5 centimeters, or 100 centimeters. And A3 is W3H3, which is, well, it's actually the same thing as A1, because it's got the same dimensions. A1, which is 60 centimeters. So by inspection, 5 centimeters, 5 centimeters, and 12 centimeters, 12 centimeters. Alright, so A is the total of them all. Looking at this equation, continuing it right here, that's 60 centimeters, and just substituting values into this expression, plus 100 centimeters, plus another 60 centimeters, or A is 220 centimeters, and of course it's centimeters squared. All these areas, centimeters squared. Put parentheses around the word so you recognize it's 10 to the minus 2 meters that all gets squared, so it's actually 10 to the minus 4 meters squared if we need to worry about that. But the areas, the units are going to cancel out because I'm going to have A1 with 60 centimeters squared. It's got units of centimeters squared divided by A, also centimeters squared. Okay, I think I might just be in a position to continue this guy. I think probably better copy it down so that you can see it. I think I'll take advantage of the fact that I'm working on a computer here. Go edit, copy, and then too far. Edit, paste. So I got another copy of the X bar that I've been working with from well above. And let's go ahead and substitute what we have learned. Did I already change that to the areas business? No. But what we proved was that M1 over M is equal to A1 over A total, and that goes for all of them. So this is A1 over A times X1 plus A2 over A times X2 plus A3 over A times X3. Which makes sense in that the mass is proportional to the area, so for both of them it would be sigma A1 is the same thing as mass 1, sigma A is the same thing as the total mass of the entire plate, and the sigmas cancel out, that constant of proportionality, and the same thing for all the terms. Alright, that was 60 centimeters squared divided by, what was it, 220 centimeters squared times x1 which was 2.5 centimeters, all the way up here near the top. So 2.5 centimeters, and then plus A2, which was that bottom piece. A2, 100 centimeters squared, and the X2 for that one was 10 centimeters, so 100 times 10. And then all divided by that 220 centimeters squared. And then plus, we got one more term, that one, same ratio as this, 60 centimeters squared divided by 220 centimeters squared. And then that one, the X3, was 17.5 centimeters. Okay, plug those numbers into the calculator and I get 10 centimeters. And it's a good thing because I can actually tell by inspection that the answer is 10 centimeters. This thing is symmetric, left to right. If I split it right down the middle, so the center of mass has to lie somewhere around there. You know, this piece over here, I got one the same exact distance over to the right, and then this one is symmetric about the center. So I would expect it to be at 10 centimeters just by inspection. Now the other one, I can't tell where it is. It's going to be, you know, it's below these two and above this one, certainly not at the mid-level of the whole square outline. It's somewhat below the center of that because I got more material on the bottom and I'm missing a lot from the top area. But so the Y one I can't tell by inspection, and this is the one that the calculations are important for. So we will, however, wind up with the same kind of expression that we had down here. I don't have to go through that business with the mass being proportional to the area again. I'll just write down Y bar is equal to A1 over A times Y1, the position of the center of mass of object number 1, and then same thing for the other two, just add a couple more terms there. So it looks just like the expression up here, except the x's have been replaced with y's. And now I got to substitute things in. Fortunately, I can just look up here to get the three multipliers. Y bar is 60 centimeters squared over 220 centimeters squared, and then times something, whatever Y1 is. I want to look those up later. I'll go ahead and keep on copying this stuff down. We do see, you know, these centimeters canceled out, so we get all these centimeters squared cancel out, and all we get is centimeters left in each term. And so the units did work out there. So plus, and then 60 over the 220 centimeters all squared. And I need more room to write the value in this. So now I need the positions x1, y1, I'm sorry, y1, y2, and y3. 11, 2.5, 11. So it's 11, 2.5, 11. Centimeters. It's 11 centimeters multiplying this whole fraction. And then let's have a crack at evaluating that on the calculator. And I get 7.136 centimeters, or to 2 sig figs, 7.1 centimeters. Let's see if that makes sense in this picture. 5, and then a little bit up from there. Certainly don't want to go as high as these guys, which were at 11. Okay, a little bit above this, a couple of centimeters above that. That makes sense. So the center of mass that was 10 point centimeters, show the 2 sig figs, comma 7.1 centimeters.